So for this very short video, we're going to introduce summation notation. This is very important for Riemann sums and the Riemann integral for this course, but it'll also be important for future courses as well. So let's go ahead and get our motivation to start with. So suppose we want to sum the first 100 integers, so 1 plus 2 plus 3, all the way up to 100. So one way we can write this is we can just write this out as 1 plus 2 plus 3 plus ... plus 100. So this way works okay because this is a fairly simple expression, but this method becomes pretty unwieldy to write it like this if we have more complicated expressions. So we'd like a more compact notation that works better for keeping track of complicated summations. So this same summation, the 1 plus 2 plus 3 and so on up to 100, we can write this more compactly in this notation here. So let's explain what this notation's meaning here. So this j here in the bottom, this is telling us what our variable is going to be. So that says j is going to change. The fact where we read it j equals 1 means our first term is going to be when j is equal to 1. And this top here, this 100, tells us when we stop. And we're going to step from j equals 1 to j equals 100 by moving the integer 1 each time. So we'll go j equals 1, j equals 2, j equals 3, and so on until we get to j equals 100. And then what the overall notation means is you start with j equals 1 and you evaluate this expression at j equals 1. Then you go to j equals 2 and you evaluate this expression at j equals 2, and so on all the way up to the top term, which is 100, and then you add all of those terms up. So it's exactly what we had before, the 1 plus 2 plus 3, and so on all the way up to 100. So this is a nice compact expression for this. Let's go ahead and see a few more examples of this to see how this works. So just to get used to the notation, let's look at what this expression here means. So from the last slide, we should see this starts when j equals 5, and then moves to j equals 6, and then moves to j equals 7, and since the top of the expression is 7, that's where we stop. And at each term, we're going to evaluate this at the number and then add them all together. So the first one will be when j is equal to 5, second one when j is equal to 2, and the last one will be when j is equal to 7. So we see here, here's the term when it's equal to 5, term when it's equal to 6, term when it's equal to 7, and then we add all of those up and we get 131. So let's look at a couple more examples here. So let's consider this sum given by 2 minus 4 plus 8 minus 16 plus 32. And suppose we want to take this and we want to write it in summation notation. So we need to find a pattern to be able to do that. So we can notice first, what does each term in this sum look like? Well, the first one is 2 to the 1. The second one, if we ignore the signs for now, 4 is 2 squared, 8 is 2 cubed, 16 is 2 to the 4th, 32 is 2 to the 5th. So that sees we kind of step up by the power each time. And then notice we alternate signs, so it's positive, negative, positive, negative, positive. So this first one is 2 to the 1, but I want it to be a positive sign, so I can think of that as minus 1 to the 1 plus 1. And then with the 1 here going with the 2 as well. In the second term we need a negative, but we have the 2 squared, so we take the power of the 2 and we add 1 to it with the power, a negative 1 raised to that, and that will give us our negative 4. Third term, take the power of the 2, add 1 to it on top of the negative 1, and that'll give me my positive 8, and so on. So we see then that 2 minus 4 plus 8 minus 16 plus 32 is given by this sum. This is a fairly complicated one to write there, but it's good practice that basically to change one of these explicit sums into summation notation, we basically have to figure out what the patterns are as we go. So let's go ahead and see one more example that's more of the form we're going to see with Riemann sums. So let's consider the function x squared, and we're going to take terms xj, which are given by 2j over 5, and we're going to set delta x to be 2/5. So if we want to evaluate this sum here, f of xj delta x, and we want to go from j equals 0 to 4. So the first thing we do is we plug in our function. So f of x is x squared, so this will give me xj squared. Now we're going to go ahead and plug in our values. So xj is 2j over 5, so we plug that in for the xj. The delta x we said is 2/5, so this goes here for the delta x. Now if we evaluate this, I'm going to get a 4j squared on the top here times 2, so that's 8j squared. And the bottom I get 25 times 5, so that's 125. And now we just go ahead and evaluate this. So you can think of this 8 over 125 isn't changing as j changes. But then this summation is saying we start when j equals 0, we increment all the way up to j equals 4, and we're squaring those. So I get 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared, and that gives me 72 over 45 once I simplify. So that's the type of summation we're going to see more in Riemann sums. So good to get used to these.